Climate change and agriculture are interrelated processes, both of which take place on a global scale. Climate change affects agriculture in a number of ways, including through changes in average temperatures, rainfall, and climate extremes. Changes in pests and diseases. Changes in atmospheric carbon dioxide and ground-level ozone concentrations. Changes in the nutritional quality of some foods. And changes in sea level. Climate change is already affecting agriculture, with effects unevenly distributed across the world. Future climate change will likely negatively affect crop production in low-latitude countries, while effects in northern latitudes may be positive or negative. Climate change will probably increase the risk of food insecurity for some vulnerable groups, such as the poor. Agriculture contributes to climate change by anthropogenic emissions of greenhouse gases, and by the conversion of non-agricultural land into agricultural land. Agriculture, forestry and land use change contributed around 20 to 25% to global annual emissions in 2010. There are a range of policies that can reduce the risk of negative climate change impacts on agriculture, and to reduce GHG emissions from the agriculture sector. Impact of climate change on agriculture. Despite technological advances, such as improved varieties, genetically modified organisms, and irrigation systems, weather is still a key factor in agricultural productivity, as well as soil properties and natural communities. The effect of climate on agriculture is related to variabilities in local climates rather than in global climate patterns. The Earth's average surface temperature has increased by 1.5 degrees Fahrenheit since 1880. Consequently, agronomists consider any assessment has to be individually consider each local area. On the other hand, agricultural trade has grown in recent years, and now provides significant amounts of food, on a national level to major importing countries, as well as comfortable income to exporting ones. The international aspect of trade and security in terms of food implies the need to also consider the effects of climate change on a global scale. A study published in Science suggests that, due to climate change, southern Africa could lose more than 30% of its main crop, maize, by 2030. In South Asia, losses of many regional staples, such as rice, millet and maize, could top 10%. The Intergovernmental Panel on Climate Change has produced several reports that have assessed the scientific literature on climate change. The IPCC Third Assessment Report, published in 2001, concluded that the poorest countries would be hardest hit, with reductions in crop yields in most tropical and subtropical regions due to decreased water availability, and new or changed insect pest incidents. In Africa and Latin America, many rain-fed crops are near their maximum temperature tolerance, so that yields are likely to fall sharply for even small climate changes. Falls in agricultural productivity of up to 30% over the 21st century are projected. Marine life and the fishing industry will also be severely affected in some places. Climate change induced by increasing greenhouse gases is likely to affect crops differently from region to region. For example, average crop yield is expected to drop down to 50% in Pakistan according to the UKMO scenario, whereas corn production in Europe is expected to grow up to 25% in optimum hydrologic conditions. More favorable effects on yield tend to depend to a large extent on realization of the potentially beneficial effects of carbon dioxide on crop growth and increase of efficiency in water use. Decrease in potential yield is likely to be caused by shortening of the growing period, decrease in water availability and poor vernalization. In the long run, the climatic change could affect agriculture in several ways: productivity, in terms of quantity and quality of crops, agricultural practices, through changes of water use and agricultural inputs such as herbicides, insecticides and fertilizers, environmental effects, in particular in relation of frequency and intensity of soil drainage, soil erosion, reduction of crop diversity, rural space, through the loss and gain of cultivated lands, land speculation, land renunciation, and hydraulic amenities, adaptation. Organisms may become more or less competitive, as well as humans may develop urgency to develop more competitive organisms, such as flood-resistant or salt resistant varieties of rice. They are large uncertainties to uncover, particularly because there is lack of information on many specific local regions, and include the uncertainties on magnitude of climate change, the effects of technological changes on productivity, global food demands, and the numerous possibilities of adaptation. Most agronomists believe that agricultural production will be mostly affected by the severity and pace of climate change, not so much by gradual trends in climate. If change is gradual, there may be enough time for biotal adjustment. Rapid climate change, however, could harm agriculture in many countries, especially those that are already suffering from rather poor soil and climate conditions, because there is less time for optimum natural selection and adaptation. But much remains unknown about exactly how climate change may affect farming and food security, in part because the role of farmer behavior is poorly captured by crop climate models. For instance, Evan Fraser, a geographer at the University of Guelph in Ontario, Canada, has conducted a number of studies that show that the socio-economic context of farming may play a huge role in determining whether a drought has a major, or an insignificant impact on crop production. In some cases, it seems that even minor droughts have big impacts on food security, versus cases where even relatively large weather-related problems were adapted to without much hardship. Evan Fraser combines socio-economic models along with climatic models to identify a vulnerability hotspots. One such study has identified U.S. maize production as particularly vulnerable to climate change because it is expected to be exposed to worse droughts, but it does not have the socio-economic conditions that suggest farmers will adapt to these changing conditions. Observed impacts. So far, the effects of regional climate change on agriculture have been relatively limited. Changes in crop phenology provide important evidence of the response to recent regional climate change. Phenology is the study of natural phenomena that recur periodically, and how these phenomena relate to climate and seasonal changes. A significant advance in phenology has been observed for agriculture and forestry in large parts of the Northern Hemisphere. Droughts have been occurring more frequently because of global warming, and they are expected to become more frequent and intense in Africa, Southern Europe, the Middle East, most of the Americas, Australia, and Southeast Asia. Their impacts are aggravated because of increased water demand, population growth, urban expansion, and environmental protection efforts in many areas. Droughts result in crop failures and the loss of pasture grazing land for livestock. Projections. As part of the IPCC's fourth assessment report, Schneider et al. Projected the potential future effects of climate change on agriculture. With low to medium confidence, they concluded that for about a 1 to 3 degrees Celsius global mean temperature increase there would be productivity decreases for some cereals in low latitudes, and productivity increases in high latitudes. In the IPCC fourth assessment report, low confidence means that a particular finding has about a 2 out of 10 chance of being correct, based on expert judgment. Medium confidence has about a 5 out of 10 chance of being correct. Over the same time period, with medium confidence, global production potential was projected to increase up to around 3 degrees Celsius, very likely decrease above about 3 degrees Celsius. Most of the studies on global agriculture assessed by Schneider et al. Had not incorporated a number of critical factors, including changes in extreme events, or the spread of pests and diseases. Studies had also not considered the development of specific practices or technologies to aid adaptation to climate change. The U.S. National Research Council assessed the literature on the effects of climate change on crop yields. USNRC stressed the uncertainties in their projections of changes in crop yields. Their central estimates of changes in crop yields are shown above. Actual changes in yields may be above or below these central estimates. USNRC also provided and estimated the likely range of changes in yields. Likely means a greater than 67% chance of being correct, based on expert judgment. The likely ranges are summarized in the image descriptions of the two graphs. Food security. The IPCC fourth assessment report also describes the impact of climate change on food security. Projections suggested that there could be large decreases in hunger globally by 2080, compared to the 2006 level. Reductions in hunger were driven by projected social and economic development. For reference, the Food and Agriculture Organization has estimated that in 2006, the number of people undernourished globally was 820 million. 3 scenarios without climate change projected 100 to 130 million undernourished by the year 2080, while another scenario without climate change projected 770 million undernourished. Based on an expert assessment of all of the evidence, these projections were thought to have about a 5-10 chance of being correct. The same set of greenhouse gas and socio-economic scenarios were also used in projections that included the effects of climate change. Including climate change, 3 scenarios projected 100 to 380 million undernourished by the year 2080, while another scenario with climate change projected 740 to 1,300 million undernourished. These projections were thought to have between a 2-10 and 5-10 chance of being correct. Projections also suggested regional changes in the global distribution of hunger. By 2080, Sub-Saharan Africa may overtake Asia as the world's most food-insecure region. This is mainly due to projected social and economic changes, rather than climate change. Individual studies. Klein looked at how climate change might affect agricultural productivity in the 2080s. His study assumes that no efforts are made to reduce anthropogenic greenhouse gas emissions, leading to global warming of 3.3 degrees Celsius above the pre-industrial level. He concluded that global agricultural productivity could be negatively affected by climate change, with the worst effects in developing countries. Lobel et al. Assessed how climate change might affect 12 food-insecure regions in 2030. The purpose of their analysis was to assess where adaptation measures to climate change should be prioritized. They found that without sufficient adaptation measures, South Asia and South Africa would likely suffer negative impacts on several crops which are important to large food-insecure human populations. Battisti and Naylor looked at how increased seasonal temperatures might affect agricultural productivity. Projections by the IPCC suggest that with climate change, high seasonal temperatures will become widespread, with the likelihood of extreme temperatures increasing through the second half of the 21st century. Battisti and Naylor concluded that such changes could have very serious effects on agriculture, particularly in the tropics. They suggest that major, near-term, investments in adaptation measures could reduce these risks. Climate change merely increases the urgency of reforming trade policies to ensure that global food security needs are met, said C. Bellman, ICTSD Programs Director. A 2009 ICTSD-IPC study by Jody Keene suggests that climate change could cause farm output in sub-Saharan Africa to decrease by 12% by 2080, although in some African countries this figure could be as much as 60%, with agricultural exports declining by up to 1/5 in others. Adapting to climate change could cost the agriculture sector $14 billion globally a year, the study finds. Regional equals. Africa. In Africa, IPCC projected that climate variability and change would severely compromise agricultural production and access to food. This projection was assigned high confidence. Africa's geography makes it particularly vulnerable to climate change, and 70% of the population rely on rain-fed agriculture for their livelihoods. Tanzania's official report on climate change suggests that the areas that usually get 2 rainfalls in the year will probably get more, and those that get only 1 rainy season will get far less. The net result is expected to be that 33% less maize the country's staple crop will be grown. Asia. In East and Southeast Asia, IPCC projected that crop yields could increase up to 20% by the mid-21st century. In Central and South Asia, projections suggested that yields might decrease by up to 30%, over the same time period. These projections were assigned medium confidence. Taken together, the risk of hunger was projected to remain very high in several developing countries. More detailed analysis of rice yields by the International Rice Research Institute forecast 20% reduction in yields over the region per degree Celsius of temperature rise. Rice becomes sterile if exposed to temperatures above 35 degrees for more than 1 hour during flowering and consequently produces no grain. A 2013 study by the International Crops Research Institute for the Semi-Arid Tropics aimed to find science-based, pro-poor approaches and techniques that would enable Asia's agricultural systems to cope with climate change, while benefiting poor and vulnerable farmers. The study's recommendations ranged from improving the use of climate information in local planning and strengthening weather-based agro-advisory services, to stimulating diversification of rural household incomes and providing incentives to farmers to adopt natural resource conservation measures to enhance forest cover, replenish groundwater and use renewable energy. A 2014 study found that warming had increased maize yields in the Heilongjiang region of China had increased by between 7 and 17% per decade as a result of rising temperatures. Australia and New Zealand. Hennessy et al. Assessed the literature for Australia and New Zealand. They concluded that without further adaptation to climate change, projected impacts would likely be substantial. By 2030, production from agriculture and forestry was projected to decline over much of southern and eastern Australia, and over parts of eastern New Zealand. In New Zealand, initial benefits were projected close to major rivers and in western and southern areas. Hennessy et al. Placed high confidence in these projections. Europe, with high confidence, IPCC projected that in southern Europe, climate change would reduce crop productivity. In Central and Eastern Europe, forest productivity was expected to decline. In Northern Europe, the initial effect of climate change was projected to increase crop yields. Latin America. The major agricultural products of Latin American regions include livestock and grains, such as maize, wheat, soybeans, and rice. Increased temperatures and altered hydrological cycles are predicted to translate to shorter growing seasons, overall reduced biomass production, and lower grain yields. Brazil, Mexico and Argentina alone contribute 70 to 90% of the total agricultural production in Latin America. In these and other dry regions, maize production is expected to decrease. A study summarizing a number of impact studies of climate change on agriculture in Latin America indicated that wheat is expected to decrease in Brazil, Argentina and Uruguay. Livestock, which is the main agricultural product for parts of Argentina, Uruguay, southern Brazil, Venezuela, and Colombia, is likely to be reduced. Variability in the degree of production decrease among different regions of Latin America is likely. For example, one study that estimated future maize production in Latin America predicted that by 2055 maize in eastern Brazil will have moderate changes while Venezuela is expected to have drastic decreases. Suggested potential adaptation strategies to mitigate the impacts of global warming on agriculture in Latin America include using plant breeding technologies and installing irrigation infrastructure. Climate justice and subsistence farmers in Latin America equals. Several studies that investigated the impacts of climate change on agriculture in Latin America suggest that in the poorer countries of Latin America, agriculture composes the most important economic sector and the primary form of sustenance for small farmers. Maize is the only grain still produced as a sustenance crop on small farms in Latin American nations. Scholars argue that the projected decrease of this grain and other crops will threaten the welfare and the economic development of subsistence communities in Latin America. Food security is of particular concern to rural areas that have weak or non-existent food markets to rely on in the case food shortages. According to scholars who considered the environmental justice implications of climate change, the expected impacts of climate change on subsistence farmers in Latin America and other developing regions are unjust for two reasons. First, subsistence farmers in developing countries, including those in Latin America, are disproportionately vulnerable to climate change. Second, these nations were the least responsible for causing the problem of anthropogenic-induced climate. According to researchers John F. Morton and T. Roberts, disproportionate vulnerability to climate disasters is socially determined. For example, socio-economic and policy trends affecting smallholder and subsistence farmers limit their capacity to adapt to change. According to W. Ban Efgen, who studied the vulnerability of Latin American agriculture to climate change, A history of policies and economic dynamics has negatively impacted rural farmers. During the 1950s and through the 1980s, high inflation and appreciated real exchange rates reduced the value of agricultural exports. As a result, farmers in Latin America received lower prices for their products compared to world market prices. Following these outcomes, Latin American policies and national crop programs aim to stimulate agricultural intensification. These national crop programs benefited larger commercial farmers more. In the 1980s and 1990s, low world market prices for cereals and livestock resulted in decreased agricultural growth and increased rural poverty. In the book, Fairness and Adaptation to Climate Change, the authors described the global injustice of climate change between the rich nations of the North, who are the most responsible for global warming, and the southern poor countries and minority populations within those countries who are most vulnerable to climate change impacts. Adaptive planning is challenged by the difficulty of predicting local-scale climate change impacts. An expert that considered opportunities for climate change adaptation for rural communities argues that a crucial component to adaptation should include government efforts to lessen the effects of food shortages and famines. This researcher also claims that planning for equitable adaptation and agricultural sustainability will require the engagement of farmers in decision-making processes. North America, a number of studies have been produced which assess the impacts of climate change on agriculture in North America. The IPCC Fourth Assessment Report of Agricultural Impacts in the region cites 26 different studies. With high confidence, IPCC projected that over the first few decades of this century, moderate climate change would increase aggregate yields of rain-fed agriculture by 5–20%, but with important variability among regions. Major challenges were projected for crops that are near the warm end of their suitable range or which depend on highly utilized water resources. Droughts are becoming more frequent and intense in arid and semi-arid western North America as temperatures have been rising, advancing the timing and magnitude of spring snowmelt periods and reducing river flow volume in summer. Direct effects of climate change include increased heat and water stress, altered crop phenology, and disrupted symbiotic interactions. These effects may be exacerbated by climate changes in River Iao, and the combined effects are likely to reduce the abundance of native trees in favor of non-native herbaceous and drought-tolerant competitors, reduce the habitat quality for many native animals, and slow litter decomposition in nutrient cycling. Climate change effects on human water demand and irrigation may intensify these effects. United States, the U.S. Global Change Research Program assessed the literature on the impacts of climate change on agriculture in the United States. Many crops will benefit from increased atmospheric CO2 concentrations and low levels of warming, but higher levels of warming will negatively affect growth and yields. Extreme events will likely reduce crop yields. Weeds, diseases and insect pests benefit from warming, and will require more attention in regards to pest and weed control. Increasing CO2 concentrations will reduce the land's ability to supply adequate livestock feed. Increased heat, disease, and weather extremes will likely reduce livestock productivity. According to a paper by Deschenes and Greenstone, predicted increases in temperature and precipitation will have virtually no effect on the most important crops in the U.S. Polar regions. Anisimov et al. Assessed the literature for the polar region. With medium confidence, they concluded that the benefits of a less severe climate were dependent on local conditions. One of these benefits was judged to be increased agricultural and forestry opportunities. For The Guardian newspaper, Brown reported on how climate change had affected agriculture in Iceland. Rising temperatures had made the widespread sowing of barley possible, which had been untenable 20 years ago. Some of the warming was due to a local effect via ocean currents from the Caribbean, which had also affected fish stocks. Small islands. In a literature assessment, Mamura et al. Concluded that on small islands, subsistence and commercial agriculture would very likely be adversely affected by climate change. This projection was assigned high confidence. Poverty impacts researchers at the Overseas Development Institute have investigated the potential impacts climate change could have on agriculture, and how this would affect attempts at alleviating poverty in the developing world. They argued that the effects from moderate climate change are likely to be mixed for developing countries. However, the vulnerability of the poor in developing countries to short-term impacts from climate change, notably the increased frequency and severity of adverse weather events, is likely to have a negative impact. This, they say, should be taken into account when defining agricultural policy. Mitigation and adaptation in developing countries. The Intergovernmental Panel on Climate Change has reported that agriculture is responsible for over a quarter of total global greenhouse gas emissions. Given that agriculture Euro unregistered trademark S share in global gross domestic product is about 4%, these figures suggest that agriculture is highly greenhouse gas intensive. Innovative agricultural practices and technologies can play a role in climate mitigation and adaptation. This adaptation and mitigation potential is nowhere more pronounced than in developing countries where agricultural productivity remains low. Poverty, vulnerability and food insecurity remain high. And the direct effects of climate change are expected to be especially harsh. Creating the necessary agricultural technologies and harnessing them to enable developing countries to adapt their agricultural systems to changing climate will require innovations in policy and institutions as well. In this context, institutions and policies are important at multiple scales. Travis Libert and Daniel Sumner suggest 6 policy principles. The best policy and institutional responses will enhance information flows, incentives and flexibility. Policies and institutions that promote economic development and reduce poverty will often improve agricultural adaptation and may also pave the way for more effective climate change mitigation through agriculture. Business as usual among the world. A Euro unregistered trademark S poor is not adequate. Existing technology options must be made more available and accessible without overlooking complementary capacity and investments. Adaptation and mitigation in agriculture will require local responses, but effective policy responses must also reflect global impacts and interlinkages. Trade will play a critical role in both mitigation and adaptation, but will itself be shaped importantly by climate change. The Agricultural Model Intercomparison and Improvement Project was developed in 2010 to evaluate agricultural models and intercompare their ability to predict climate impacts. In Sub-Saharan Africa and South Asia, South America and East Asia, AgMIP regional research teams are conducting integrated assessments to improve understanding of agricultural impacts of climate change at national and regional scales. Other AgMIP initiatives include global gridded modeling, data and information technology tool development, simulation of crop pests and diseases, site-based crop climate sensitivity studies, and aggregation and scaling. Crop development models. Models for climate behavior are frequently inconclusive. In order to further study effects of global warming on agriculture, other types of models, such as crop development models, yield prediction, quantities of water or fertilizer consumed, can be used. Such models condense the knowledge accumulated of the climate, soil, and effects observed of the results of various agricultural practices. They thus would make it possible to test strategies of adaptation to modifications of the environment. Because these models are necessarily simplifying natural conditions, it is not clear whether the results they give will have an in-field reality. However, some results are partly validated with an increasing number of experimental results. Other models, such as insect and disease development models based on climate projections, are also used. Development scenarios are used in order to estimate climate change's effects on crop development and yield. Each scenario is defined as a set of meteorological variables, based on generally accepted projections. For example, many models are running simulations based on doubled carbon dioxide projections, temperatures ranging from 1 degree Celsius up to 5 degrees Celsius, and with rainfall levels an increase or decrease of 20%. Other parameters may include humidity, wind, and solar activity. Scenarios of crop models are testing farm-level adaptation, such as sowing date shift, climate-adapted species, irrigation and fertilizer adaptation, resistance to disease. Most developed models are about wheat, maize, rice and soybean. Equals temperature potential effect on growing period equals, duration of crop growth cycles are above all, related to temperature. An increase in temperature will speed up development. In the case of an annual crop, the duration between sowing and harvesting will shorten. The shortening of such a cycle could have an adverse effect on productivity because senescence would occur sooner. Equals effect of elevated carbon dioxide on crops equals, carbon dioxide is essential to plant growth. Rising CO2 concentration in the atmosphere can have both positive and negative consequences. Increased CO2 is expected to have positive physiological effects by increasing the rate of photosynthesis. This is known as carbon dioxide fertilization. Currently, the amount of carbon dioxide in the atmosphere is 380 parts per million. In comparison, the amount of oxygen is 210,000 ppm. This means that often plants may be starved of carbon dioxide as the enzyme that fixes CO2, or ubisco, also fixes oxygen in the process of photospiration. The effects of an increase in carbon dioxide would be higher on C3 crops than on C4 crops, because the former is more susceptible to carbon dioxide shortage. Studies have shown that increased CO2 leads to fewer stomata developing on plants, which leads to reduced water usage. Under optimum conditions of temperature and humidity, the yield increase could reach 36%, if the levels of carbon dioxide are doubled. A study in 2014 posited that CO2 fertilization is underestimated due to not explicitly representing CO2 diffusion inside leaves. Further, few studies have looked at the impact of elevated carbon dioxide concentrations on whole farming systems. Most models study the relationship between CO2 and productivity in isolation from other factors associated with climate change, such as an increased frequency of extreme weather events, seasonal shifts, and so on. In 2005, the Royal Society in London concluded that the purported benefits of elevated carbon dioxide concentrations are likely to be far lower than previously estimated when factors such as increasing ground-level ozone are taken into account. Effect on quality. According to the IPCC's TAR, the importance of climate change impacts on grain and forage quality emerges from new research. For rice, the amylose content of the grain a major determinant of cooking quality is increased under elevated CO2. Cooked rice grain from plants grown in high CO2 environments would be firmer than that from today's plants. However, concentrations of iron and zinc, which are important for human nutrition, would be lower. Moreover, the protein content of the grain decreases under combined increases of temperature and CO2. Studies using FACE have shown that increases in CO2 led to decreased concentrations of micronutrients in crop plants. This may have knock-on effects on other parts of ecosystems as herbivores will need to eat more food to gain the same amount of protein. Studies have shown that higher CO2 levels led to reduced plant uptake of nitrogen, resulting in crops with lower nutritional value. This would primarily impact on populations in poorer countries less able to compensate by eating more food, more varied diets, or possibly taking supplements. Reduced nitrogen content in grazing plants has also been shown to reduce animal productivity in sheep, which depend on microbes in their gut to digest plants, which in turn depend on nitrogen intake. Agricultural surfaces and climate changes equals. Climate change may increase the amount of arable land in high-latitude region by reduction of the amount of frozen lands. A 2005 study reports that temperature in Siberia has increased 3 degrees Celsius in average since 1960. However, reports about the impact of global warming on Russian agriculture indicate conflicting probable effects. While they expect a northward extension of farmable lands, they also warn of possible productivity losses and increased risk of drought. Sea levels are expected to get up to 1 meter higher by 2100, though this projection is disputed. A rise in the sea level would result in an agricultural land loss, in particular in areas such as Southeast Asia. Erosion, submergence of shorelines, salinity of the water table due to the increased sea levels, could mainly affect agriculture through inundation of low-lying lands. Low-lying areas such as Bangladesh, India and Vietnam will experience major loss of rice crop if sea levels rise as expected by the end of the century. Vietnam, for example, relies heavily on its southern tip, where the Mekong Delta lies, for rice planting. Any rise in sea level of no more than a meter will drown several km2 of rice paddies, rendering Vietnam incapable of producing its main staple and export of rice. Erosion and fertility equals. The warmer atmospheric temperatures observed over the past decades are expected to lead to a more vigorous hydrological cycle, including more extreme rainfall events. Erosion and soil degradation is more likely to occur. Soil fertility would also be affected by global warming. However, because the ratio of carbon to nitrogen is a constant, a doubling of carbon is likely to imply a higher storage of nitrogen in soils as nitrates, thus providing higher fertilizing elements for plants, providing better yields. The average needs for nitrogen could decrease, and give the opportunity of changing often costly fertilization strategies. Due to the extremes of climate that would result, the increase in precipitations would probably result in greater risks of erosion, whilst at the same time providing soil with better hydration, according to the intensity of the rain. The possible evolution of the organic matter in the soil is a highly contested issue, while the increase in the temperature would induce a greater rate in the production of minerals, lessening the soil organic matter content, the atmospheric CO2 concentration would tend to increase it. Potential effects of global climate change on pests, diseases and weeds equals. A very important point to consider is that weeds would undergo the same acceleration of cycle as cultivated crops, and would also benefit from carbonaceous fertilization. Since most weeds are C3 plants, they are likely to compete even more than now against C4 crops such as corn. However, on the other hand, some results make it possible to think that weed killers could gain in effectiveness with the temperature increase. Global warming would cause an increase in rainfall in some areas, which would lead to an increase of atmospheric humidity in the duration of the wet seasons. Combined with higher temperatures, these could favor the development of fungal diseases. Similarly, because of higher temperatures and humidity, there could be an increased pressure from insects and disease vectors. Glacier retreat and disappearance equals, the continued retreat of glaciers will have a number of different quantitative impacts. In the areas that are heavily dependent on water runoff from glaciers that melt during the warmer summer months, a continuation of the current retreat will eventually deplete the glacial ice and substantially reduce or eliminate runoff. A reduction in runoff will affect the ability to irrigate crops and will reduce summer stream flows necessary to keep dams and reservoirs replenished. Approximately 2.4 billion people live in the drainage basin of the Himalayan rivers. India, China, Pakistan, Afghanistan, Bangladesh, Nepal and Myanmar could experience floods followed by severe droughts in coming decades. In India alone, the Ganges provides water for drinking and farming for more than 500 million people. The west coast of North America, which gets much of its water from glaciers in mountain ranges such as the Rocky Mountains and Sierra Nevada, also would be affected. Ozone and UVB equals. Some scientists think agriculture could be affected by any decrease in stratospheric ozone, which could increase biologically dangerous ultraviolet radiation B. Excess ultraviolet radiation B can directly affect plant physiology and cause massive amounts of mutations, and indirectly through changed pollinator behavior, though such changes are not simple to quantify. However, it has not yet been ascertained whether an increase in greenhouse gases would decrease stratospheric ozone levels. In addition, a possible effect of rising temperatures is significantly higher levels of ground-level ozone, which would substantially lower yields. ENSO effects on agriculture equals, ENSO will affect monsoon patterns more intensely in the future as climate change warms up the ocean's water. Crops that lie on the equatorial belt or under the tropical Walker circulation, such as rice, will be affected by varying monsoon patterns and more unpredictable weather. Scheduled planting and harvesting based on weather patterns will become less effective. Areas such as Indonesia where the main crop consists of rice will be more vulnerable to the increased intensity of ENSO effects in the future of climate change. University of Washington professor, David Battisti, researched the effects of future ENSO patterns on the Indonesian rice agriculture using IPCC's 2007 annual report and 20 different logistical models mapping out climate factors such as wind pressure, sea level, and humidity, and found that rice harvest will experience a decrease in yield. Barley and Java, which holds 55% of the rice yields in Indonesia, will be likely to experience 10% probably of delayed monsoon patterns, which prolongs the hungry season. Normal planting of rice crops begin in October and harvest by January. However, as climate change affects ENSO and consequently delays planting, harvesting will be late and in drier conditions, resulting in less potential yields. Impact of agriculture on climate change. The agricultural sector is a driving force in the gas emissions and land use effects thought to cause climate change. In addition to being a significant user of land and consumer of fossil fuel, agriculture contributes directly to greenhouse gas emissions through practices such as rice production and the raising of livestock. According to the Intergovernmental Panel on Climate Change, the three main causes of the increase in greenhouse gases observed over the past 250 years have been fossil fuels, land use, and agriculture. Land use equals, agriculture contributes to greenhouse gas increases through land use in four main ways: CO2 releases linked to deforestation, methane releases from rice cultivation, methane releases from enteric fermentation in cattle, nitrous oxide releases from fertilizer application. Together, these agricultural processes comprise 54% of methane emissions, roughly 80% of nitrous oxide emissions, and virtually all carbon dioxide emissions tied to land use. The planet's major changes to land cover since 1750 have resulted from deforestation in temperate regions. When forests and woodlands are cleared to make room for fields and pastures, the albedo of the affected area increases, which can result in either warming or cooling effects, depending on local conditions. Deforestation also affects regional carbon reuptake, which can result in increased concentrations of CO2, the dominant greenhouse gas. Land clearing methods such as slash and burn compound these effects by burning biomatter, which directly releases greenhouse gases and particulate matter such as soot into the air. Livestock and livestock-related activities such as deforestation and increasingly fuel-intensive farming practices are responsible for over 18% of human-made greenhouse gas emissions, including 9% of global carbon dioxide emissions, 40% of global methane emissions, 64% of global nitrous oxide emissions. Livestock activities also contribute disproportionately to land use effects, since crops such as corn and alfalfa are cultivated in order to feed the animals. Worldwide, livestock production occupies 70% of all land used for agriculture, or 30% of the land surface of the earth. See also: aridification, biochar, desertification, environmental issues with agriculture, fisheries and climate change, food security, global warming and wine, International Assessment of Agricultural Science and Technology for Development addressing the links between climate change and agriculture, Land Allocation Decision Support System a research tool that is used to test how climate change may affect agriculture, retreat of glaciers since 1850, slash and char, terra preta, water crisis, climate resilience. Notes. References, Annex INC, 6th National Communications from parties included in Annex I to the Convention including those that are also parties to the Kyoto Protocol, United Nations Framework Convention on Climate Change. Archived August 2, 2014. Battisti, David. Naylor, Historical Warnings of Future Food Insecurity with Unprecedented Seasonal Heat, Science 323, 240 4, doi, 10.1126/Science 1164363, PMID 19131626, retrieved April 13, 2012. Klein, W.R., Global Warming and Agriculture, Finance and Development 45. Archived August 17, 2014. HLPE, Food Security and Climate Change. A report by the high-level panel of experts on food security and nutrition of the Committee on World Food Security, Rome, Italy, Food and Agriculture Organization of the United Nations. Archived December 12, 2014. Hoffman, U., ed., Trade and Environment Review 2013, Wake Up Before It Is Too Late, Make Agriculture Truly Sustainable Now for Food Security in a Changing Climate, Geneva, Switzerland, United Nations Conference on Trade and Development, ISSN 1810-5432. Archived November 28, 2014. IPCC AR5WG2A, Field, CB. AL, eds., Climate Change 2014, Impacts, Adaptation, and Vulnerability. Part A, Global and Sectoral Aspects. Contribution of Working Group 2 to the 5th Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press. Also available at IPCC Working Group 2. Archives, Main IPCC website, December 16, 2014. IPCC WG2, November 5, 2014. IPCC AR5WG3, Edenhofer, O. AL, eds., Climate Change 2014, Mitigation of Climate Change. Contribution of Working Group 3 to the 5th Assessment Report of the Intergovernmental Panel on Climate Change, Cambridge University Press. Also available at mitigation2014.org. Archives, Main IPCC website, November 27, 2014. Mitigation2014.org, December 30, 2014. Lobel, David. Burke, Tebaldi, Mastrandrea, Falcon, Naylor, Prioritizing Climate Change Adaptation Needs for Food Security in 2030, Science 319, 607 €10, doi, 10.1126/Science 1,152,339, PMID 18,239,122, retrieved April 13, 2012. Lobel, D. A.L., Prioritizing Climate Change Adaptation Needs for Food Security, Policy Brief, Center on Food Security and the Environment, Stanford University CS1 Maintenance, Explicit Use of A.L. Archived September 27, 2014. Non-Annex INC, Non-Annex I National Communications, United Nations Framework Convention on Climate Change. Archived September 13, 2014. USNRC, Climate Stabilization Targets, Emissions, Concentrations, and Impacts Over Decades to Millennia, Washington, D.C., USA, National Academies Press. Further reading, Fisher G., Shao M. and Van Veldhuizen H. Climate Change and Agricultural Vulnerability. International Institute for Applied Systems Analysis. Report prepared under UN Institutional Contract Agreement 1113 for World Summit on Sustainable Development. Laxenburg, Austria, Climate Change Pushing Coffee to Extinction? October 17, 2011, Rosenzweig, Cynthia and Daniel Hillel ed. Handbook of Climate Change and Agroecosystems, The Agricultural Model into Comparison and Improvement Project Integrated Crop and Economic Assessments. Imperial College Press/World Scientific Publishing. External links, Climate Change on the Food and Agriculture Organization of the United Nations website. A comprehensive report on the relationship between climate change, agriculture and food security by the International Food Policy Research Institute. See also an overview of IFPRI's climate change research. Climate Change, Rice and Asian Agriculture, 12 Things to Know. Asian Development Bank, LADSS. Climate Change and Agriculture. Are we asking the right questions? Food security of women in the context of climate change. Online discussion forum, The Guardian's, Climate Change Coverage. http www.guardian.co. Climate change often includes discussions about food security, including the 30 June 2005 article, 1 in 6 countries facing food shortage, How is climate change threatening agriculture? Section of official popularized version of IAASTD synthesis report, Impacts of Climate Change on European Forests and Options for Adaptation report to the European Commission Directorate General for Agriculture and Rural Development. Report written by European Forest Institute with University of Natural Resources and Life Sciences, Vienna, Institute of Forest Entomology, Forest Pathology and Forest Protection, INRA Euro-UMA Biodiversità Copyright Garnese Common Author Copyright S and Accademia Italiana di Scienze Climate Change and Agriculture in the ECA region. A regional look by the World Bank at climate change and agriculture in countries in Europe and Central Asia. Climate Change, Agriculture and Food Security global scientific research program that seeks to overcome the threats to agriculture and food security in a changing climate, exploring new ways of helping vulnerable rural communities adjust to global changes in climate. Meat Eater's Guide to Climate Change plus Health Life Cycle Assessment of Greenhouse Gas Emissions associated with 20 types of meat, fish, dairy and vegetable proteins, as well as these foods. Unregistered trademark effects on health. Climate farming first. Climate changes. Falls in agricultural productivity of up to 30% over the 21st century are projected. Marine life and the fishing industry will also be severely affected in some places. Climate change induced by increasing greenhouse gases is likely to affect crops differently from region to region. For example, average crop yield is expected to drop down to 50% in Pakistan according to the UKMO scenario, whereas corn production in Europe is expected to grow up to 25% in optimum hydrologic conditions. More favorable effects on yield tend to depend to a large extent on realization of the potentially beneficial effects of carbon dioxide on crop growth and increase of efficiency in water use. Decrease in potential yield is likely to be caused by shortening of the growing period, decrease in water availability and poor vernalization. In the long run, the climatic change could affect agriculture in several ways: productivity, in terms of quantity and quality of crops, agricultural practices, through changes of water use and agricultural inputs such as herbicides, insecticides and fertilizers, environmental effects, in particular in relation of frequency and intensity of soil drainage, soil erosion, reduction of crop diversity, rural space, through the loss and gain of cultivated lands, land speculation, land renunciation, and hydraulic amenities, adaptation. Organisms may become more or less competitive, as well as humans may develop urgency to develop more compatible properties and natural communities. The effect of climate on agriculture is related to variabilities in local climates rather than in global climate patterns. The Earth's average surface temperature has increased by 1.5 degree Fahrenheit since 1880. Consequently, agronomists consider any assessment has to be individually consider each local area. On the other hand, agricultural trade has grown in recent years, and now provides significant amounts of food, on a national level to major importing countries, as well as comfortable income to exporting ones. The international aspect of trade and security in terms of food implies the need to also consider the effects of climate change on a global scale. A study published in Science suggests that, due to climate change, Southern Africa could lose more than 30% of its main crop, maize, by 2030. In South Asia, losses of many regional staples, such as rice, millet and maize could top 10%. The Intergovernmental Panel on Climate Change has produced several reports that have assessed the scientific literature on climate change. The IPCC Third Assessment Report, published in 2001, concluded that the poorest countries would be hardest hit, with reductions in crop yields in most tropical and subtropical regions due to decreased water availability, and new or changed insect pest incidents. In Africa and Latin America, many rain-fed crops are near their maximum temperature tolerance, so that yields are likely to fall sharply for even small. Climate change and agriculture are interrelated processes, both of which take place on a global scale. Climate change affects agriculture in a number of ways, including through changes in average temperatures, rainfall, and climate extremes. Changes in pests and diseases. changes in atmospheric carbon dioxide and ground-level ozone concentrations, changes in the nutritional quality of some foods, and changes in sea level. Climate change is already affecting agriculture, with effects unevenly distributed across the world. Future climate change will likely negatively affect crop production in low-latitude countries, while effects in northern latitudes may be positive or negative. Climate change will probably increase the risk of food insecurity for some vulnerable groups, such as the poor. Agriculture contributes to climate change by anthropogenic emissions of greenhouse gases, and by the conversion of non-agricultural land into agricultural land. Agriculture, forestry and land use change contributed around 20 to 25% to global annual emissions in 2010. There are a range of policies that can reduce the risk of negative climate change impacts on agriculture, and to reduce GHG emissions from the agriculture sector. Impact of climate change on agriculture. Despite technological advances, such as improved varieties, genetically modified organisms, and irrigation systems, weather is still a key factor in agricultural productivity, as well as soil-petitive organisms, such as flood-resistant or salt-resistant varieties of rice. They are large uncertainties to uncover, particularly because there is lack of information on many specific local regions, and include the uncertainties on magnitude of climate change, the effects of technological changes on productivity, global food demands, and the numerous possibilities of adaptation. Most agronomists believe that agricultural production will be mostly affected by the severity and pace of climate change, not so much by gradual trends in climate. If change is gradual, there may be enough time for biotal adjustment. Rapid climate change, however, could harm agriculture in many countries, especially those that are already suffering from rather poor soil and climate conditions, because there is less time for optimum natural selection and adaptation. But much remains unknown about exactly how climate change may affect farming and food security, in part because the role of farmer behavior is poorly captured by crop climate models. For instance, Evan Fraser, a geographer at the University of Guelph in Ontario, Canada, has conducted a number of studies that show that the socio-economic context of farming may play a huge role in determining whether a drought has a major, or an insignificant impact on crop production. In some cases, it seems that even minor droughts have big impacts on food security, versus cases where even relatively large weather-related problems were adapted to without much hardship. Evan Fraser combines socio-economic models along with climatic models to identify a vulnerability hotspots. One such study has identified U.S. maize production as particularly vulnerable to climate change because it is expected to be exposed to worse droughts, but it does not have the socio-economic conditions that suggest farmers will adapt to these changing conditions. Observed impacts. So far, the effects of regional climate change on agriculture have been relatively limited. Changes in crop phenology provide important evidence of the response to recent regional climate change. Phenology is the study of natural phenomena that recur periodically, and how these phenomena relate to climate and seasonal changes. A significant advance in phenology has been observed for agriculture and forestry in large parts of the Northern Hemisphere. Droughts have been occurring more frequently because of global warming, and they are expected to become more frequent and intense in Africa, Southern Europe, the Middle East, most of the Americas, Australia, and Southeast Asia. Their impacts are aggravated because of increased water demand, population growth, urban expansion, and environmental protection efforts in many areas. Droughts result in crop failures and the loss of pasture grazing land for livestock. Projections. As part of the IPCC's fourth assessment report, Schneider et al. Projected the potential future effects of climate change on agriculture. With low to medium confidence, they concluded that for about a 1 to 3 degrees Celsius global mean temperature